Hello, this is the SJ20 buck boost converter, 20 amps MPPT. It looks like that. So this buck boost converter is based on the, takes the display board off, LT8705. So here's the chip. It's the Linear Technologies LT8705. Interesting pin arrangement. It's got lots of pins, but sort of some missing from the middle of the top row there. So this is a complex chip. It pretty much does everything, and that means that there's not a huge amount else on this board. Underneath there are just 4 MOSFETs. It's a 4 MOSFET topology buck boost. There's a big fat current sensing resistor there, and here there's an op amp. OPA 1612, that is. That looks like a regulator. Over here there's a little step down buck power supply. It's based on the XL, what is it, 7015 I think it is, and that appears to generate 5 volts for this fan connector here, and it does seem to me from my tests that a fan may well be necessary. Single inductor, even though this is buck or boost, a couple of big diodes and some capacitors. These are 330, 100 volt, 105 degrees C. Linear Technology LT8705, 80 volt V in and V out, 4 switch buck boost DC-DC controller. So it uses 4 n-channel MOSFETs. It has the gate drivers for those, and a single inductor which allows a V out above or below the V in. It's synchronous rectification, so you get very high efficiency. This works similarly to the LTC3780, also I think by Linear Technology. But this has additional circuitry in it. It has 4 feedback control loops built in for output voltage, output current, input voltage and input current. Now I've been waiting for an LT8705 module for quite some time, and they have been around, but they have tended to be very expensive. And although this is not digitally controlled, it's got 3 potentiometers, so it's potentiometer controlled. It does have a digital display which kind of acts as lots of multimeters attached to the input and the output. You can see output voltage, output current, input voltage. You can also see on the display the MPPT set point. Now this MPPT is interesting. It's not maximum power point tracking. It just targets a certain voltage, so I call it maximum power point targeting. But I'll power this up now and we'll take a little look at what we can see on this display. Right, first things first, XT60 to terminal block adapter so that we can feed power in from a power bank. So I've got a power bank down here with a cigarette lighter output, so we can get 12 volts or thereabouts at a reasonable current, up to about 10 amps I think. Right, let's switch on the power bank and see what appears on the display. Okay, so at the moment it's showing the output voltage. That's adjustable with this potentiometer. It also shows the output current. There isn't any at the moment because I've not got anything connected. You can also display the input voltage, so we've got 12.9 volts coming from the power bank. And you can also display this. It's in CEV. Now it uses the centigrade or Celsius indicator here, but they call it input constant voltage. And this is the voltage you set for MPPT targeting. Now I'm probably not going to do solar panel input in this video, but this buck boost converter is ideally suited to solar panel on the input and a battery on the output. Right, I'm going to put this bulb on the output, 24 volt brake light bulb for a truck or lorry, mainly because the power bank keeps shutting its 12 volt output off in the absence of any current drawn. So we just want to draw a bit of current to keep that on. Right, let's turn the power bank back on. I've got this set so that it... Oh, that's interesting. Why did that turn off? Oh, it's gone into current limiting at 400 milliamps. Yes, that's not very bright, is it? Yeah, I've got this set to automatically come on when the power is applied, the output to come on. You can disable that. Press and hold this button and it says out off. So now when I power up the input to this device, let's turn it off, turn it back on again. It will power up the electronics, but it won't switch the output on. Okay, I need to set a reasonable output current. Now, like I say, oh, the input's turned off again. Yeah, that's because I didn't have my bulb actually on. Okay, let's turn the 12 volts of the power bank back on. Turn on the lamp. There's a bit of a pulse output there, isn't there? Give it a reasonable current. In fact, let's not limit the current at all. Now this is, as I say, only a monitor. You can only see what's going on. You can't preset values on it. So we've got output is 18.6 volt. This is a 24 volt bulb. And the current is 800 milliamps. There is a constant current LED down there if it's lit, but it's incredibly dim. If it's lit, then you know it's in current limiting. So let's go into current limiting. That's current limiting. There's the LED, the little red one above this red LED. You can see it's lit, but it's often very dim. So we can see output voltage, and I can adjust that. Now this is in boost mode, of course, at the moment, because the input voltage is 12.7 now. The output voltage is 19.9. I can safely take that all the way up to about 24 for this particular bulb. I can also take that down past the 1-to-1 voltage point, which is 12 volts, and put it into buck mode so that the output voltage is lower than the input voltage. Now, if you're not using the MPPT function or the input voltage feedback control loop, you want to set it in a arrangement like this. You want to set it to a voltage, so we'll go to the in CV, a voltage below that which is coming in on the input. So we'll set that down to 11 volts, and that way it won't interfere with the output control loops, the voltage control loop, which, as I say, I can adjust with this pot to increase the brightness of the bulb, and the current control loop, which is adjusted with the CC pot. Okay, let's switch off the output, remove the bulb, and put on the output. Is that hot? Yeah, a little bit. Put on the output this supercapacitor module, which has been heavily modified. It has got little LEDs on each protection circuit. It's got some terminal posts. It's got a nice analog meter which shows that currently it's at about 2.5 volts. So let's put that there and we'll charge that up. I'll get some wires hooked up, and then we can watch the voltage climb slowly all the way from 2.5 volts to 16.2, I think is the maximum of this module. There's no problem connecting batteries or supercapacitors to the output of this thing, because you've got the MOSFET here, inductor between them, and one MOSFET points one way and the other MOSFET, in terms of the body diodes, points the other way, so you can't get a feed through the unit from output to input. What will happen when I connect this is that the voltage on the supercap, 2.5 volts, it's not enough actually. It will backfeed into these output capacitors and also into the little green LED here, which is simply strapped across the output. So the green LED on the output can be backfed from a battery or a capacitor on the output. But let's get the input in now and start charging that supercap. Right, I've balanced the supercap module on a piece of blue tack. Switch on the power bank. And what we need is an output voltage at least as high as the 16.2. Oh, you can see the current output voltage because yes, it backfeeds to the point where the microcontroller measures the output voltage. What was it set to? About 20 something, I think, but that's probably all right. What I might need to do is bring down the current, but let's just turn it on, and the output voltage is climbing up. Oh, we got 2 amps. Now that's going to overwhelm the protection circuits on the supercap, so I'll bring that down. Well, I'll leave it where it is for the moment so we can watch the voltage on the supercap module rise up. But the supercapacitor module has these discharge circuits, which is 10 ohms in parallel with 10 ohms. That's 5 ohms, and these are 2.7 volt. Let's call it 2.5. So that's 2.5 volts, 5 ohms. So that's half an amp. So when these turn on, they can dissipate half an amp of current. So what I want to do is charge this supercap module at less than half an amp, so that these protection circuits are capable of offsetting all of the incoming current. And the power bank shut off once again. Oh, because I haven't got that switched on. So let's wind the current limit down. So now I'm using the output current feedback control loop. I'm not using the output voltage feedback control loop because that's set way over the 8 volts of this supercap bank. So I'll bring this down to 400 milliamps. So that we know that we're not going to overwhelm, so yeah, 0.4, we're not going to overwhelm these protection circuits. And now we can see the voltage rising up on the supercap module. You can see it's about 9 volts there. It's 9 volts indicated here. We can also look at the input voltage. That's the power bank input voltage coming on through this XT60 here. So that's 12.9. We can also look at this input constant voltage. So that's the MPPT set point, which is set on this temperature. So that feedback control loop is not in use at the moment. We can look at current on the output, which is 400 milliamps. If you press and hold this button for a few seconds, you can also see it as watts on the output. So that's about 4 watts. Yeah, 10 volts, 400 milliamps is 4 watts. You can go back to amps now. And so now I'm going to wait. I'll tell you what I'll do. I'll keep filming and I'll speed this section up. Wait for this to rise up to 16 and a bit volts, and then you should see the blue LEDs coming on this supercap module. Actually, I'll talk through this bit. Okay, so I think this is a very versatile module because you can have a solar panel on the input where you can target the voltage on the solar panel. So even if you're charging a 24 volt battery, you can set this pot to target the solar panel voltage at, I don't know, 17, 18 volts, whatever gives you maximum power. You can also have a battery on the input and a battery on the output, or you could have a battery on the input and a load on the output, like this light bulb, for example, or something a bit beefier. Okay, I seem to have set the voltage limit too low because the power's dropped off to almost nothing. So let's just raise that up a bit. And now it's current limiting. You can see the current limiting part is the little lid there. It's very dim, as I say. And now the protection circuits on the supercapacitor module are coming on, and they will offset the full 400 milliamps because they are dumping 500 milliamps or more, actually, because these are 2.7 volts into the two 10 ohm resistors in parallel. So I'll just run this shot for a bit so we get a nice little light show on these 6 protection circuit LEDs. Right, what I'm going to do now is add into the mix this little relay, this voltage controlled relay unit. I'll put the lamp on here, and what we'll do is when the supercap gets up to a certain voltage, we'll turn the relay on, thus turning the lamp on. This lamp draws about an amp, I think, at this sort of voltage. So it will offset the half amp or the 400 milliamps coming into the caps and drain them down, and the relay will just turn on and off and we'll have a flashing lamp. So I want the voltage controlled relay module in those two terminals, and then I want the super cap. I've taken the super cap off because I don't want it shorting out and there being a loud bang. So I want the super cap also across the output. Get in there. Okay, so the relay module is in parallel with the super cap. Let's put the super cap back on. Now there's going to be a little spark, I think, here, because there's 16 volts on this and the output capacitors are now down to 0 volts really. So let's just see what happens. Yeah, a little spark. Oh, that voltage has triggered this thing. Oh, we can't see that because can't see the display. I'll get it set up so we can see it. This has turned off again because the power bank has turned off because there's no current being drawn. Okay, there we are. That's all working. So 400 milliamps current limit on this SJ20 power supply, charging the supercapacitor. When that gets up to 16 volts, so 15.8, 15.9, when that gets up to 16 volts, relay turns on, turns this lamp on. That puts about a 1 amp load on the supercap, so its voltage then falls down. The lower voltage on this is set to 15.5, I think. That's the point where the relay drops out, allows the supercap to charge back up at this 400 milliamps, and the cycle repeats. Now you should see that the voltages on these two devices are the same. So 15.8, yeah, 15.9. This has actually got 2 decimal places, whereas the relay module has only got 1 decimal place. But yeah, so charging the supercap up to a voltage, discharging it back because of the lamp down to a lower voltage, and oscillating. Yeah, okay, so now you can see the voltages a little bit better. You can see the needle on the supercap module. The blue LEDs on the supercap module won't come on now because at 16 volts, which is below the point where they come on, this light bulb comes on and then the voltage on the supercap comes back down. But I'll just run this for a few minutes now at high speed so you can watch the bulb come on and off and flash, although you can't see the bulb very well. So let me turn that around like that, but I want to be able to see the voltage on there and the bulb. That'll do. So that's the ZK-SJ20 buck boost power supply. Now 400 milliamps is not a high current. In fact, this thing's cold. The heatsink's cold. I've run this up to 10 amps and it started to get quite warm. And one thing I noticed particularly was the output capacitors were getting quite hot. The input capacitors were getting warm. Now possibly this is because the series pass MOSFETs are down here and the top of the MOSFET is sitting on the underside of this PCB. So I'm not sure that the positioning of these capacitors is optimum. The other thing is there's a heatsink here stuck along the underside of where the chip is, and the chip also says in the datasheet that it has to be soldered down. There's an underbelly pad on it and it has to be soldered down to the PCB, so presumably the chip gets quite warm. I haven't checked that yet. There is this 5-volt fan port. There are 4 mounting points here, so you could put standoffs there to raise this thing up, and I've purchased a couple of 50mm fans. I'm going to experiment with putting those on this unit to keep it cool. When I was running it at 10 amps I had just a standalone fan blowing air on this, and that did seem to work. So in another video I'm just trying to be careful not to short things. I will do solar panel on the input and the use of this MPPT pot. Now, just to mention here that if you want to get this MPPT function to work, or at least to get it to target a certain voltage, so one of my solar panels I know is 17 volts, you have to make sure that neither of the output control loops is being used. So you have to make sure that the CV pot is set high enough. Say you're charging a battery, you set the CV pot higher than the voltage of the battery, and you set the CC pot high enough that it doesn't current limit on the output. And that's fine because you're current limiting on the input, of course, because the solar panel has a maximum current beyond which it can't go. So by virtue of how solar panels work, you're current limiting on the input. So as long as you're not using the output feedback loops, the MPPT pot thing will work. You might want to use the CV pot so that you don't overcharge the battery, but then of course when the battery is fully charged, you don't want maximum power from your solar panel. You want that to back off so that you don't overcharge the battery. But I'll do more on MPP and MPPT and solar, using a solar panel on the input, because the other issue is what happens at night. This whole unit powers down and then you get the very slow rise of voltage and current on the input at the beginning of the day. Does this thing boot reliably? And of course that I haven't yet tested. But yeah, that's the first look at the ZK-SJ20 buck boost using the LT87705. Yeah, just another buck boost really. Cheerio.